Here is an explanation for the answer to final exam. Question number 86 in Electronics Demystified 2nd edition. If you have the printed book, you'll find it on page 436. We're talking here about a device called a silicon photodiode. This is basically a semiconductor diode, ordinary silicon semiconductor diode. But this junction has a clear region around it so that radiant energy can actually strike this junction. If there is no radiant energy, particularly visible light, infrared, or ultraviolet, striking this device, and we reverse bias it, that is, we put a plus polarity on the N-type semiconductor and a minus polarity on the P-type semiconductor, we'll get the same behavior as we would expect with an ordinary silicon semiconductor diode. These white dots represent holes, which are positive charge carriers. They are attracted to the negative polarity away from the junction. These little black dots here represent electrons, negative charge carriers attracted to the positive polarity, also away from the junction. So that creates this depletion region right around the junction, which acts more or less like the dielectric in a capacitor and prevents the diode from conducting. Well, with an ordinary diode, of course, it's opaque. You shine a light on it and nothing happens. But in the case of a silicon photodiode, if we shine radiant energy on this thing, visible light, ultraviolet, or infrared particularly, even X-rays will do it, strikes this junction, and that causes something very interesting to happen. It causes this depletion region to vanish. When that happens, the diode conducts something like the avalanche effect, except it conducts to an extent that varies according to the brilliance. Well, radiant energy, referring to visible light, ultraviolet, or infrared. The brilliance or the intensity of that radiant energy affects the extent to which this device will conduct. Well, what is that phenomenon good for? Well, it acts like a variable resistor, in effect. We can use it to create a light meter, a light intensity meter, also known as an illuminameter. But that's not any of our choices here. We can also receive modulated light signals with it, and that is one of our choices. Light here meaning also infrared or ultraviolet, because as the intensity of this radiant energy changes, the extent of the conduction changes, so we can keep this thing reverse biased and connect the output through appropriate isolation components to an audio amplifier and actually recover the modulated envelope of the signal, just like we would do with amplitude modulated radio. We can also send other modes, audio frequency shift keying, audio phase shift keying. We can send a lot of different types of modulated signals and strike this diode, and the response time is so fast that it will recover modulation frequencies up to the hundreds of kilohertz. So this is really a very effective way to receive modulated light signals. Well, that is choice C. We can also use a photovoltaic cell to do that, also known as a solar cell. But in this case, the most logical application of the choices that were given is choice C. The others really don't have any relevance to this particular type of device anyway.